So this is the last lesson of our unit. I hope that we all took some time yesterday to get started on the pretest review. If you didn't, you're going to want to make sure that you do that tonight because we have one review day tomorrow and the test is still on Monday. Is that what you're going to ask me? Yeah. Yeah, so the hope was, hopefully you saw my post on EDSB and you treated yesterday as like your first set of review day, but we still do have review tomorrow. Okay, I have two questions for you guys today. Kind of our goal in some of these problems is to use derivatives in order to do things like maximizing and minimizing. So things that we might want to maximize would be revenue, money. Things that we might want to minimize could be like the surface area of packaging, could be a certain amount of material that we use, stuff like that. So when we can minimize material, we can kind of maximize the profits that we can make from something. So we are going to find some optimal values. All right, so our first example is that we have a lifeguard that has 200 meters of rope with some buoys, with which she intends to enclose a rectangular area at the lake for swimming. The beach is one side of this rectangle, and the rope will border the other three sides. We want to find the dimensions that will produce the maximum enclosed area if there are no restrictions on the dimension, and also due to the depth of water, if we can only extend a maximum of 40 meters into the lake. Okay, so these are kind of like, we want to make sure that we can obviously keep people safe in this, but also use our material efficiently. Okay, so let's just draw a little picture to start. We've got the beach. This will be our sand color, I guess. Accuracy is important in these sketches. Okay, here's our beach. That looks like a good watercolor. And we've got some water. And we would like to run a rope just enclosing an area, a swimming area. Okay, so maybe we can call this, I don't know, the length over which we extend into the water and the width of the area. Or you can name it opposite, doesn't matter. But for our purposes, you should probably name it the same as what I name it, but it doesn't really matter which variable we choose for everything. Okay, so we have 200 meters of rope. We know that. We're going to use that in a second. I also know that the area of a rectangular section is length times width. Okay, I also know something about, because I have that 200, what is that 200 talking about in terms, like in mathematical terms, with this shape that we have here? What is the 200? What was that? Perimeter, good. So I know that perimeter, in this case right here, is going to be length and another length, so two lengths plus a width. And I know that that perimeter can be 200 meters. Okay, and the key here is that we're trying to maximize this swimming area. So we're trying to maximize the area inside of this. Now, really, the only reason that I'm using this perimeter is to, of course, incorporate that 200. And it's also so that I don't have multiple variables in my area expression. So usually what we would like to do in these cases is set up, usually we'll have two equations, and we'll set it up so that we can isolate one variable to sub into the other equation. So in this equation right here, it's really easy for me to isolate for width. So I might just take this 2L and move it to the other side, and then we'll actually plug it into our area formula.
Do you always plug into the formula you're trying to maximize?
Yeah. Yeah, so Aiden just asked, do we plug into the formula we're trying to maximize? And the answer would be yes. Okay? So this is usually just like a supporting equation that helps us with maximizing or minimizing. So this right here is going in for the width of our area formula here. Okay, so we have the formula area equals length times 200 minus 2L. And just so it's easier for us to take the derivative here, we might just expand this guy out. So again, anytime we hear maximum, minimum, stuff like that, we're thinking about the first derivative. So there's one thing that I know about this function right now. This function is already set up as, it's a quadratic, right? It has L squared, that's the highest degree. And I can see that that quadratic is opening down. So I must have a maximum on this function. So this function is already set up that we're going to get a maximum once we take the derivative and find the critical number. So we're going to find the derivative. Okay, using this function. So we're differentiating with respect to L here. So maybe we say dA over dL. That's our derivative notation. It's equal to 200 minus 4L. And again, because we're looking for a maximum, I'm looking for that critical point there. I'm looking for where this is equal to 0. So we're just going to solve for where that happens. And this is in meters. Okay, so this is our length that will potentially maximize our area. I'm also looking for the width that will maximize our area, so I'm going to plug that back into our width formula above. And it looks like we're getting 100 for width. Zainab. Yeah, we found the derivative of the area. Okay, so the dimensions that will maximize are a length of 50 meters and a width of 100 meters. Okay, there's also a second part to this question, so that was part A. Part B, hopefully I have enough space here. Part B asks us to determine if the area cannot extend more than 40 meters into the lake. So the maximum that we found, or sorry, not the area, but the length that we put as our variable here, this length right here, can't be more than 40 meters. So we just found that the optimal length is 50 meters, but we actually can't have more than 40 meters. So this is where we kind of test those endpoints, right? So I can have a length anywhere from 0 meters up to 40 meters. So of course, I don't know that it's necessary for us to test a length of 0, because we know if the length is 0, then the area is also 0, right? Then we have no section. So basically, what this question is telling us is that the length must be between 0 and 40. So if you want, you can go ahead and test a length of 0. If your length is 0, then your width is also 0 and your area is 0. So this probably is not a great option if length is 0. But if area, if our length is 40, we know that we can find our potential width here. We can also, so normally what we would do is if we have like multiple things that fall within that range, we would test it after we find the width, we would test it back in the area formula. So if my length is 40, then I know my width, why is this not working here? Thank you. Sorry, I'm just frozen here. Give me 2 seconds. There we go. Okay. Yep. The derivative gives us areas where we have turning points, right? So it gives us maxes and mins. That's why we look for derivatives to maximize and minimize things. Does that make sense? Okay, so if my length is 40, then my width is 200 minus 2 times 40, so 120. And our area here, so again, I'm just basically testing this to show you that if you have multiple things in that, you have to test the areas for those things. Because our critical number is outside of this range, this is just going to be our maximum area that we can find, which will be 120 times 40, which gives us 4,800 meters squared. So that is our maximum area that we can get. Length of 40 and width of 120. Okay, whereas in the part A, we can see that 50 times 100 would give us an optimal area, maximum area of 5,000. Okay. Cool. Okay. Second question. Any questions on that one, actually? Sorry, before we move to the last one. We're all okay with this? Maiwa? So we found the derivative, again, because when we're trying to maximize or minimize things, the derivative, where the first derivative is equal to 0, that gives us maxes and mins. So in order to optimize, the derivative helps us do that. It helps us find maximums and minimums. Well, I know from this original equation right here that I have a quadratic, it's degree 2, and I know that that quadratic is opening down because it's negative 2. So I automatically know, just from looking at that original function, that I'm getting a maximum there. Yep?
Otherwise, how would you know? Like on the quiz, do you put like the value into the second derivative?
You can do a second derivative test if you want to see if it's like concave up or concave down, for sure. Yeah. Mark?
So in B, we're like assuming right away that 40 is going to be the optimal length, right?
Yeah, because there's no critical number in there, so that tells me that there's no maximum, so the maximum must be the 40. Sarah?
If it's a quadratic and it's like opening up, like wouldn't it be a minimum?
Yeah. Yeah, so a lot of times the way that this works out is what the question is asking for is supported by how the formulas are set up. There's no reason why I would want to minimize area in here, I don't think, right? So the way that the question is set up, it will kind of ask you for the thing that makes sense to find. Okay, let's try one more. So we have a cardboard box, hard word to say, with a square base, and it's going to have a volume of 8 liters. Now you'll notice later in our question that we have some units in centimeters. So one thing that you need to know when dealing with volumes is that 8 liters is actually equivalent to 8,000 centimeters cubed, okay? So if you see that and then you see maybe like centimeters later in your question, you might want to work with that 8,000 centimeters cubed rather than 8 liters. Okay, we're going to find the dimensions that will minimize the amount of cardboard to be used. So we're thinking surface area here.
It's cubed or squared?
Cubed. Volume is cubed, right? Squared is like a flat. It's like surface area. Okay, so let's just draw ourselves a picture. We've got a square base. And then I've got, I don't know how high this goes, but we can just... Okay, so there's our little box. The base is square, so I need this depth and width here, or whatever you want to call them, to be the same variable. So maybe they are x and x. Okay, again, I know that because it said it's square, so the sides must be equal there. Height doesn't necessarily have to be the same as those, though, so we will call it h for height. Okay. Okay, so there's a couple things that we know here. We know, of course, volume is length times width times height, so that's x times h, which will give us x squared h. And we do know information about the volume. We know that the volume of the box is 8,000 centimeters cubed. Okay, we are trying to deal with surface area here, so really the only reason why I'm using this volume formula here is so that I can isolate a variable and sub it into my surface area so that I can minimize the surface area. Okay, surface area. Now we need to calculate the areas of all sides of this box. So I have a top and I have a bottom. My bottom is going to be, of course, x times x. So I will get x squared. Okay, so we'll have the top and the bottom, and also 4 sides, right? So there's my top, there's my bottom, and my 4 sides, how do I calculate the area of one side? X times h, okay, so this one's going to be 4xh, because I have 4 of those sides. Okay, and then, of course, I can say 2x squared. Okay, now the problem arises because I can't differentiate a function that has more than one variable, right? So in our first example, we differentiated with respect to L. I can't do that if I have an L and a W. Same thing here, I can't differentiate with respect to X if I also have an H in there. So my goal here is to isolate H, and then I want to sub that expression into my surface area so I have all x's, and then I can differentiate with respect to x. So I'm just going to divide out the x squared. And this expression that we just found here is what's going to be subbed in for the h in our surface area formula here. Question?
Like, if we tried to differentiate something that had 2 variables, it just wouldn't work.
That is what's called implicit differentiation, and we're going to talk about that next chapter. But yes, for now, it doesn't work.
Okay.
Yeah. Also not ideal for us if we're just like trying to find like a maximum or a minimum quickly. This will be much more efficient. Okay, let's simplify this before we take the derivative. I think I can reduce one of each of these x's in this expression here. So I'd be left with 1x on the top. And then we've got 4 times 8,000, which is going to give us 32,000. And I might just bring up this x as an x to the negative 1 here so that I can differentiate just using power rule.
Can you multiply both terms by x, and then it's 2x cubed plus 32,000?
No, because when I do that, I'd also have to multiply surface area by x. Okay, let's take the derivative so that we can find max or min. Well, in this case, minimum. The question's set up so that we can find a minimum surface area. Oh, and now I can't erase. Thank you. Smart. So I just brought this x that's down at the bottom up so that we can just use power rule. Who's that? Gabriella? I mean, I think you should know how to find like surface areas and volumes of things at this point. If it's like a cylinder, then I'll give you that, because I think that's a little tougher. But if it's just like cubes, I think that you can find stuff like that. Okay, derivative 4x minus 32,000 x to the negative 2. Yep. So by looking at the original equation, we don't necessarily know. So we actually can do a test in the second derivative, but we need to first find that critical number, or critical numbers. Well, this one's asking us to minimize the amount of cardboard. Yeah. Okay, so I'm interested in where this is equal to 0. And maybe we'll just bring that x down. Okay, so I think we can just do a little rearranging here. We'll multiply the x squared up, we'll get x cubed. And then divide out that 4, and we will get 8,000. And then I will cube root to get x by itself. Do I have to do plus minus when I cube root? Why not?
Because the negatives still.
The cube root of negative is negative.
Mm-hmm. So if I'm cube rooting a positive, it must have been a positive that we started with. Also, I'm not really interested in a negative x value here because that doesn't make sense as far as the question. X is like length. So what do we get here?
20.
Yes. 20 or, yeah, okay, that makes sense. Yep.
If you cross multiply,
You can cross multiply. Yeah, think of this as if it's over 1 and then cross. I really just multiplied the x squared up, but same idea as cross multiplication. Again, if you're unsure as to whether this for sure certainly is a minimum, you can find the second derivative and you can plug it in just to make sure that the concavity is concave up and that it is a minimum. No, you would plug 20 into your second derivative and check to see that you get positive. So yeah, if you want to do that check, you can, or if you have a graphing calculator, you can graph the original function and just see what it looks like. Those are options. Again, these questions are kind of set up so that we do get maxes and mins where we're asked for maxes and mins, right? We're not going to be asked to maximize the surface area of packaging. It doesn't make sense. You might be asked to maximize the volume, but the formulas will work so that we get those optimal values. Okay, so what is height, Mayowa?
I wasn't gonna answer that, but I just want to reaffirm that, so if it asks like minimize, like we should just see what we get, like minimize,
As long as you set everything up properly, but yeah, the formulas usually work in our favor so that we get minimums. Where we're asked for minimums and stuff like that, yeah. Okay, so what's this, 20 as well? So what is this, centimeters? Okay, so it looks like this is a cube in order to minimize that. So therefore, we want to have a cube Cool. All right, the second part of this tells us some information about cost. So the cardboard for the box costs 0.1 cents per centimeter squared, but the cardboard for the bottom is thicker, so it costs 3 times as much. So it's costing 0.3 cents per centimeter squared. We want to find the dimensions that will minimize the cost of the cardboard. So I'm going to actually work from this formula of surface area right here because I already have my top and my bottom separated out. And we're actually just going to multiply those areas by their cost per centimeter squared. So the top and the 4 sides will be at 0.1 cent. And then the bottom part, that x squared part in the middle, that will be at 0.3. So I'm multiplying each of those sections by their respective costs. Yep.
Doesn't the question just ask for the dimensions?
Yep. But we need a formula in order to do that. Yep.
Can you repeat all of that?
So why don't I just show you? Okay, so I'm going to use the surface area formula. So we talked about the top plus the bottom plus the 4 sides above. which was x squared plus 4xh. Okay, so the costs for these, my formula, maybe we'll call it C at x, is going to be 0.1 times the area of the top, plus 3 times the amount for the area of the bottom, so 0.3 for the bottom, plus 0.1 times the 4 sides. Okay, we can simplify out here a little bit. Oh, actually, I guess we can just add those guys together. So 0.4 x squared. Also, again, I don't really want to have that h in there, so we're going to replace that guy with the thing from above that we used, the formula for height. Here we go. So it will be 8,000 over x squared. So the question tells us that the cost for the bottom is 3 times as much, so 0.3 rather than 0.1. Olivia?
Did you separate the 4 from the xh because you knew
I just multiplied these together. I didn't separate it. Okay, and then I think we can just take one more step here and just simplify. So we will get 0.4 times 8,000, which is 3,200, thank you. And one of these x's will cancel with one of these x's, and maybe we'll bring that to the top again so that we can find the derivative more easily. Okay, derivative. We'll do c prime at x. And again, I'm interested, Mary, sorry.
I just wanted to clarify, are you distributing like the 0.1x4 into all of the answers?
So when I do 2 times 7 times 5, do I do 2 times 7 and 2 times 5? Or do I do 2 times 7 and then multiply that by 5? Right, so I'm not going to do 0.1 times 4 and also 0.1 times x and times h, right? I do it once. Okay, cool. So we're interested in where this is, again, equal to 0. So we'll just do a little bit of rearranging here again. So same kind of solving process as last time. We're going to get an x cubed up here. And we'll divide out that negative 0.8. You get 4,000. And then we will cube root that. Okay, let's round to maybe like 3 decimal places here. I got 15.874. Mary?
Why is that number 3200?
We did 0.4 times 8,000. So that gives you 3,200. Okay, and we plug this back in to get our height, of course. You can actually even just plug in the cube root of 4,000 down there if you want. Actually, I might just do that. 8,000 divided by answer. So I got 31.748. Therefore, the dimensions to, whoops, minimize cost R. Remember, we have x times x, so 15.874 centimeters by another one of those, because the bottom is square, by 31.748 centimeters. Okay, so I would just kind of summarize this in saying, when we do these optimization questions, we usually need two formulas. So for instance, the first one was surface area or not surface area, but just area and perimeter. This guy is like volume and surface area. So we need two things to kind of work together. Usually one of them is simply used to isolate a variable so that we have all one variable in the thing that we're trying to maximize or minimize. So here I was actually trying to minimize surface area. So I'm really just using the volume formula to plug into my surface area so that I can minimize all with one variable. Okay, that's kind of the goal. So you're going to develop two formulas depending on what information you have. Okay, also it depends on whether that's like a 2D question or a 3D question. Usually 3D you're doing volume and surface area. And then you need to plug one into the other so that you have all of one variable, find the derivative, and find where that derivative is equal to 0. Devin?
What if we set to maximize the amount of particles?
Why would we want to do that though?
I don't know, but like, how do you know it's minimizing it? Like, I still don't understand.
So again, these are kind of like, they're kind of like intuitive in the sense that like, there's no reason why we would want to maximize the surface area. We might want to maximize volume. In that case, we'd be plugging into the volume formula, right? And then I'd be finding the derivative of the volume formula.
What if I did that by accident? So you just find the derivative,
Yep.
set it to 0, and then solve for x, and then plug it back in. But how do you
Yep.
know that x is like minimizing x?
I mean, you can solve for h if you want. I'm usually just choosing the one that's easier to isolate for. And Also, like in this scenario here, it's easier for me to just isolate for the h because I only have one h in surface area. And it's also easier to isolate for that in the volume formula as well. So it doesn't matter whether you isolate for x or for h. We just want to differentiate with respect to one variable only though. That's the key. Okay? Okay, so there are 3 questions